The inauguration of the Millau Viaduct on December 14, 2004 marked the opening of one of the greatest structural accomplishments. Designed by Millau Viaduct, it holds the title as the world's highest bridge and is a cable-stayed bridge spanning over the valley of the River Tarn, with a total length of 2,460 meters long. It connects two plateaus through a slender steel deck of 8 spans and 7 pylons. From its conception to its completion, the bridge estimated a total of 400 million euros and is expected to have a lifespan of 120 years. Not only was it constructed to enhance the transportation efficiency in the surrounding regions, it serves to address a variety of social, economic, and ecological factors. Its design considers tourism and the subsequent impact of local businesses. It tackles on issues such as high wind pressures, stresses under repeated loadings, fatigue cracking, and temperature variations. Finally, it accounts for the environmental issues and a longer-lasting future in sustainability.
The concept of cable-stayed bridges began at the same time as suspension bridges and had 3 main criteria: aesthetics, economy, and performance. However, these were not very successful due to technical flaws, improper calculations, and poor aesthetics. Many designers did not approve of the unappealing combination of cable-stay parts and cable-suspended parts. Because of this, cable-stayed bridges were not rapidly developed in the beginning of the 19th century. Some of the early bridges were built in concrete, including those designed by Eduardo Torroja in the 1920s and Albert Caquot in 1952. However, these were not economical designs due to their extreme weight. They also did not perform well due to the lack of flexibility. One solution that developed was pioneered by Franz Dissinger and his German design of a series of steel bridges that crossed the River Rhine. This was pivotal in the subsequent application of cable-stayed bridges. The reason for slow development was the lack of understanding of structural integrity in the new designs. Flexible and slender bridges were a very recent development, and so the calculations were not completely accurate. The results would sometimes oppose the actual safety of the bridge, and it wasn't until many years later that engineers began to understand and solve the problems of these bridges. Once the detailed design and code requirements were understood, the international development of cable-stayed bridges progressed rapidly. In the 1990s, cable-stayed bridges entered the domain of long spans, which was previously exclusive to suspension bridges. The world record for length was continuously broken from the French Saint-Nazaire Bridge in 1975, spanning 404 meters, all the way to the Japanese Tatara Bridge in 1998, spanning 890 meters. The capability of a cable-stayed bridge more than doubled in 25 years. Other improvements include pre-stressed concrete trusses to deal with high compressive forces by the cables, economic feasibility, and more elegant design. The cable-stayed bridge has undergone a significant evolution from early collapses to some of the longest spans in the world.
Because of its immense height and many spans, the design of the Millau Viaduct is different than the traditional cable-stayed bridge. First, its deck consists of a steel orthotropic box girder. It also has triangulated cross beams in order to help spread across the forces along the temporary piers during construction. Under the traffic lanes, the steel is also a bit thicker to help prevent fatigue strains from vehicles passing over it. Also, because the bridge is so tall, the wind loads are a lot higher than normal. Because of this, windscreens are placed on the sides of the bridge to lower wind forces on vehicles passing. Also, there's a 3-meter shoulder on the edge of the bridge to prevent drivers from experiencing vertigo. As for the pavement, it is vulnerable to cracking in the top layer, which is different than normal pavement that tends to crack in the bottom. Thus, there is a 60mm asphalt layer on the top with a polymer that helps resist thermal cracking in the cold. Under that is a 3mm sealant layer which helps to reduce interaction between the asphalt layer and the deck. Finally, there's a thin primer layer that bonds the steel to the pavement. Because the bridge is split up into 8 spans, it is vulnerable to high moments because of unsymmetrical live loads and wind. Thus, the piers have to be attached rigidly to the deck in order to make it more flexible and thinner. Because the piers are rigid, it is susceptible to thermal expansion, and thus the piers need to be split up into 2 shafts at its uppermost 90 meters for flexibility. For the pylons and cables, the pylons are attached rigidly to the deck, the same as the piers, to reduce deck moments. The legs of the pylons consist of stiff box girders, and the mast is where the cables attach in a fan-like pattern. The cables themselves are protected against UV light and vibrations from wind and rain.
One of the main issues regarding the future of the Millau Viaduct is the heavy traffic. Due to its placement over the valley of the River Tarn and its appeal to tourists, the bridge amounts to approximately 20,000 vehicles per day. As a result, it plays a crucial role in the bridge's social and economic aspects, affecting local businesses and bridge maintenance, because the wear and course of the bridge demands more improved materials than those used on normal stretches. In addition, heavy traffic influences the behavior of bituminous surfacings on steel orthotropic decks, and causes the pavement to be most susceptible to fatigue. Because of repeated loadings, the surfaces must have increased durability over an expected temperature range and resistance to thermal cracking at extreme points. These effects on construction must, therefore, be monitored closely during the bridge's lifespan while also seeking transportation alternatives. The Millau Viaduct utilizes complex methods of analysis and a variety of new construction materials. Its design demonstrates an expansion of the concept of cable-stayed bridges, which pivotal leaders such as Edward Toroha and Franz Tischinger implemented in their early 20th century designs. Furthermore, the Millau Viaduct made sure to incorporate the three fundamental criteria of aesthetics, economy, and performance in both its early stages, its development, and future sustainability.